Good afternoon, everyone. We're going to go ahead and start into our unit on thermochemistry. Part of the information is going to be coming from Chapter 6, and the other part from later in the textbook. Make sure you're taking notes, and I guess we're ready to begin. Now, when we talk about energy overall, what we're talking about is the capacity to do work or produce heat. So when we deal with energy in general, usually when we say our energy is low, it means for us that we feel tired, we feel drawn down, and it'd be very difficult for us to go about doing any type of activity. When we talk about chemical systems, we think about it in the same way. In some way, we need to use the energy produced to do something, whether it's to complete a chemical reaction or just to produce any type of energy to do some other process. We talked about before our LCOE, law of conservation of energy, basically just tells us that all the energy that is here, that is around us, that is quote unquote created in a chemical reaction wasn't really created, it was really just transformed. It came from one form to another and it continued that change throughout its life cycle until, because energy is constant. We have our two different types of energy we always talk about, potential and kinetic. We've dealt with these before. And just a little bit of a diagram to help us understand. Looking at our first object, we'll say object A, which has a higher potential energy than ball B, but once it's released, it will actually cause ball B to move along the hill and end up at a higher potential energy than A had. Now, heat involves the transfer of energy between two objects. So if I put an ice cube next to a hot piece of steel, the heat is going to transfer from the hot piece of steel into the ice. In the process, that's actually work being done on the ice. So if the ice is our system, as we'll talk about in just a second, we're going to look at the fact that the temperature is going to change, it's going to begin to melt, and those types of things. Now, energy is what we call a state function. So it doesn't really depend on where it started. It is. Okay. Now, when we look at work and heat, these are not. These actually have signs. They have a value associated with them. Energy overall is, it just is. Now, when we deal with chemical energy, we have to look at system and surroundings. And I've been saying this a lot throughout this whole process. The system is whatever it is that we're going to focus on at that time, whether it be a specific reaction, a specific part of the reaction, a specific item in a room. The surroundings include everything else, including the humans that are in the room, or the thermometer, anything that we're using to measure the change in energy of that system. We can tell whether energy leaves the system or has to be added to the system using a couple of different words, endothermic or exothermic. Endothermic, heat is into the system. These will usually feel cold to the touch because it'll begin to pull the heat right out of your hand. Or there are things that are exothermic, which will give off heat. So when you feel them, they'll be warm to the touch. Now, don't get these things confused. If we're looking at the system overall, an endothermic process, because it is taking in heat, the system itself is warmer. Whereas an exothermic process, because the heat is being given off, the system itself is going to be cooler. This is why we'll look at something like ice melting as being an endothermic process, but ice forming or freezing being an exothermic process. Now, when we look at how this energy changes forms, we would actually say that we're studying thermodynamics. Thermo, heat, dynamics, change. We're looking at how it changes throughout overall systems. When we try to measure the internal energy of a system, what we're really looking at is the potential energy of all of the particles that are there. And we use this little formula, delta E equals Q, which is our heat, and W, which is our work, to understand what's going on with the internal energy of a system. Now, it has our thermodynamic quantities, our energy values, have to have two things: the magnitude, which is a number. So if I see 1 joule versus 150 joules, I know there's a big difference. And then a sign that lets us know which direction the energy is going, in or out of the system. Always, we're going to look at it from the system's point of view. So if delta E is less than 0 or negative, that means it's going to be exothermic. Whereas if it's positive, that means energy is coming into the system. It's an endothermic process. We do the same thing when it comes to work. When the system does work on the surroundings, W is going to be negative. When the surrounding does work on the system, it's going to be positive. The easiest way I think about this one when it comes to work is I look at if I have to go. I remember I used to always have to go and rake leaves and do all these different odd jobs. When I did that, I came back and I was tired. I was exhausted. I expended so much energy. That will be the same as the system doing work on the surroundings in some way. Whereas if someone was doing work on me, say I was relaxing, so I was getting a haircut or a massage or something like that, then that's going to leave me revitalized. It's going to give me more energy to be able to proceed. So again, system doing work or does the work, then it's going to be negative. Surrounding does the work on the system, W will be positive. Overall, we can take this information in dealing with gases specifically and understand that if we have a cylinder with a piston inside, we can measure the amount of work using this formula that's given here. If the gas expands, meaning the volume increases, we know that there was actually work being done by the system. But if it decreases based on what's happening outside of the cylinder, we know that it's going to be positive, because the system is actually the surroundings are doing work on the system. Now, enthalpy. Enthalpy is also what we call a state function. It's looking at the Q value, or the heat, at a constant pressure. Okay? Now, if we want to find delta H, or change in enthalpy, we're going to look at it just like we have before: H of products minus H of reactants. We go even more specifically to look at calorimetry, because this gives us an idea of how this energy change occurs in an isolated system. Now, calorimetry overall, you see, is the science of measuring heat, and we have to use this thing called specific heat capacity. Now, if we're looking at specific heat capacity, we're looking at the energy required to raise 1 gram of substance 1 degree Celsius. We've dealt with this one before. This was the one where we had the joules over grams times Celsius. There's another way that you'll see it, and it also will be molar heat capacity. Now, this is the amount needed to raise 1 mole of a substance. Now, what's the difference between 1 gram and 1 mole? Depending on the substance, that is a very, very large difference. And so either way, we're just monitoring how much energy it is that is required for each change, each incremental change that we can utilize. Now, if I have, and this is where we kind of ended off on Friday, if I have two reactants, same temperature, and they're mixed, and the solution gets warmer, what's happening? Well, if they started off the same temperature, we mix, that means that energy has to be released from somewhere. But where's that energy coming from? Well, if you remember before, we talked about chemical energy and looking at what's in those bonds that we've always been talking about this whole year so far. If I take these two things, mix them together, boom, things begin to get warmer. I can already understand that there are some bonds that are probably being broken. When those bonds are broken, that energy is released. If it's an endothermic process, and we expect it to go the opposite direction. So we'd expect the temperature to go down because the energy is being pulled from the surroundings and even from the thermometer itself. Now, we'll deal a little bit with a coffee cup calorimeter. This is just an easy way for us to observe reactions and see what's actually going to happen with time. Very simple construction. when we study calorimetry, we will use what we did before in class. Q equals MC delta T. Here they actually have the specific heat as S. For all intents and purposes, you can use S, but as we've talked about before, C, lowercase c, is what we're going to deal with here. Now, this is where we're actually going to end this first video before we get into Hess's law and the other things. Take a moment, look back over the notes, look at the examples that we've done. One of the key things I want you to understand is it's not just about being able to do the math, but it's also about understanding what the process is behind it. Why is it that these things are changing the way that they are? Well, that's where we're going to end it for now. I will talk to you all and see you in class. Have a great day.